So now it's time to get to how we're actually going to use Pollard row to factor things. So at the end of the day, the real genius part of Pollard row is the fast collision detection part that we've already talked about. And both the Pollard row algorithm for factoring and the Pollard row algorithm for discrete logs that we're about to talk about are really at their heart based on the fast collision detection that we've already talked about. But each of the Pollard row factoring and the Pollard row discrete log algorithms have their own ways of taking advantage of the fast collision detection in order to be able to factor or calculate discrete logs. So my goal here is to factor a composite number n. And I'm going to warn you right up front, you can only feed a composite number to this factoring algorithm. And that's actually true of most factoring algorithms. Most factoring algorithms are not capable of proving that a number is prime. They're only capable of finding factors of a number that's not prime. Now, fortunately, you can be quite certain a number is composite before you hand it to the factoring algorithm, because that's the half of the Fermat test, remember, that always works. So if the Fermat test tells you a number is composite, it's definitely composite. You can go ahead and feed it to Pollard row, see what happens. So let's start with the basic idea of how we're going to apply the Pollard row collision algorithm to factor n. So we're going to start with our path from Pollard row like before, where we're going to take our stone path here, and this path is going to be of numbers mod n, and we're going to generate them, again, by coming up with a function from the numbers mod n to the numbers mod n, and so that function is usually going to be something of the form x squared plus c mod n, where this c is just some constant. And so again, as soon as I pick my first step, x0, and the c, the rest of the path is completely determined, just like we've been talking about. And so the rest of the path is then forced to have this sort of row shape. But I'm actually not really interested in finding a collision here mod n. I'm actually interested in finding a collision mod p. But what's p? Well, here p is a prime divisor of n. So in other words, I'm not looking for two spots on the path where, say, x2 and x14 are equal. I'm looking for two spots on the path where, say, x2 and x14 are equal mod p for some p that divides n. Now, how am I going to catch that two numbers are equal mod a divisor of n? Well, we get to use our old friend, the Euclidean algorithm. Namely, we're going to detect this by calculating the GCD of the difference of 2 points on the path and n. And so if xi and xj agree mod p, xi minus xj is divisible by p, n's also divisible by p, and so this GCD is divisible by p. And so our hope here is to use this Pollard row rapid collision detection algorithm in order to find a time where xi and xj collide mod p, and then use the fact that we can calculate the GCD of xi minus xj with n to find p. So to initialize this, we're going to pick our starting point x0 and our function f as above. And so again, as soon as I've picked these, I've laid out my path, and I'm going to just send the turtle and the rabbit along the path that's already dictated completely by x0 and f, because again, x1 is f of x0, x2 is f of x1, and so on down the line. Then, as the last part of our initialization, we're going to put the rabbit and the turtle on the starting point. Okay, so once we have initialized the algorithm, then we're going to run into an iterated loop, just as we described for Pollard row in general, where we're going to repeatedly move the turtle 1 step forward, move the rabbit 2 steps forward, and then we want to ask the turtle and rabbit if they're looking at the same number. But remember, we don't actually want to know if xi and xj or whatever, we don't actually want to know if those numbers are equal. We want to know if they're equal mod p. So to actually uncover that, we're going to calculate the GCD of the turtle's number minus the rabbit's number with n. Now, based on what the answer is here, we're going to do one of several different things. So if that GCD is 1, which is what I expect to happen most of the time, then I'm just going to start the next iteration. It is possible that when you calculate this GCD, you'll get n. Unfortunately, if this happens, the algorithm has failed. And so if you run into this state, then what do you have to do? Well, you have to go back to the start. And so when I say reinitialize here, you're going to pick a new x0, and you're probably going to pick a new f as well, just to give yourself a fighting chance. Again, I want to stress, this is very unlikely to happen in any instance where the number you're factoring is large enough that you actually want to be using a factoring algorithm to do it. But, actually, if this GCD is anything other than 1 and n, well, then I have a number that divides n that's not 1 or n, which means I have a proper factor of n. And so then I can just return this GCD, because this GCD is going to be now a factor of n. Now, when I went over this in class, someone sort of rightly pointed out to say, have I really finished factoring n at this point? And, well, the answer is maybe not, because maybe the factor I found isn't prime, or maybe if I divide out that factor, the number that's left isn't prime. But if that's the case, it's easy enough to run a primality test on those two pieces, and if either or both of them aren't prime, just run this algorithm again. And note, the number that you're dealing with is now smaller, so the algorithm is likely now to be even faster. So, completely factoring a number is always a recursive process where I start with some number, check if it's prime. If it's prime, I'm done. If it's not prime, then I find a proper factor of it, and then repeat with the proper factor and the quotient. And so, once you know how to do this algorithm where you take a number that's not prime and find a proper factor of it, then you're in good shape to completely factor whatever number you want. Now, I'll show you some examples of this in a minute, but I want to think about how long this is going to take. So remember, we're comparing this as a factoring algorithm to trial division, which was O of n to the 1/2. Now, if you think about birthday algorithm stuff, you might be inclined to think, oh, well, this is also going to be O of square root of n, because that's how long it takes to find a repetition, or to find a collision, is something on the order of the square root of n. If that were the case, that would be really bad. But actually, this algorithm, remember, I'm not looking for a collision mod n, I'm looking for a collision mod p. So this is actually not O of square root of n, it's O of square root of p. Which p? Well, really any p that divides n, but the one that's going to make this the smallest is the smallest prime that divides n. Now, what this really means is n could be absolutely enormous, and yet this algorithm could still be very efficient if one of the prime factors of n is small. But if you sort of imagine the sort of like the worst possible shape that n could have, well, n could be a product of two primes that are roughly the same size, and in that case, you would end up with something that is O of, well, how big would p be in that instance? Well, p would be about the size of the square root of n, and so you would end up here with the square root of the square root of n, which ends up being n to the 1/4. So if you have no idea what the shape of your number is, you can end up getting something that's O of n to the 1/4. If your number has smaller prime factors and you know that, then you actually might get something that's much faster than that. But that really is the magnitude of the improvement between trial division and Pollard row factoring, is that we went from something that was n to the 1/2 to something that was n to the 1/4. And as you'll see when we do examples in a moment, this is really, really much faster. So let's pull up Sage and see it go to town with this particular algorithm. This, by the way, is still all posted to the 361 Sage account, so if you go to Pollard row examples, you can play with any of these functions and whatnot. You can make fun of my poor programming skills, whatever you like. So to demonstrate this, I'm going to have Sage generate a number that is a product of two random primes less than 10,000. So roughly speaking, this should be a product of two 4-digit primes. Should be looking at an 8-digit number here that we can then run this algorithm on. We get a little summary here that shows us the number we factored and the factor that we found. And it also tells us how many iterations that we needed, which is the same as this number of GCDs we computed, and we computed here 74 GCDs. Now, whenever you look at one of these little reports at the end of this algorithm, what you should mentally do is you should think, okay, how many iterations would trial division have taken? Well, I'd have divided by 2, then by 3, then by 4, then by 5, then by 6, and so on, until I divided by 2,591, and when I divided by 2,591, at that iteration, I would have found this factor with trial division. So, roughly speaking, trial division would have taken 2,591 iterations in order to find this factor. However, our algorithm here, Pollard row, took only 74 iterations in this particular instance. I want to draw your attention here in this turtle and rabbit story to the last line here. Note again, the turtle and rabbit here at the end are not equal to each other. But what is true is that they're equal to each other mod 2,591. And so the way this algorithm finally ended is that it calculated the GCD of the difference of the rabbit and the turtle's number with n and found, oh, that's 2,591, and 2,591 is therefore a factor of this number. Just to draw your attention back here at the top, you can see this has the same rabbit-turtle structure that we're used to, where, again, there's a path laid out with each of these numbers on each pebble along the path, and the turtle and rabbit are proceeding down the same path, but the rabbit is going twice as fast as the turtle. And so, for example, if you look where the rabbit is sitting 3 iterations in, at this number, well, that's where the turtle will be, but not 3 iterations in, 6 iterations in. So, now that we understand what the turtle and rabbit are doing, let's look at a bunch of runs of this at once, but we're just going to suppress the turtle and rabbit's places along the path so that we can just look at this. Now, I want to note for you here, when I run this 10 times, I'm keeping the same number rather than picking a new number to factor each time. And so in this instance, you can see that the number that it chose to factor is 1,277 times 5,281. And one thing that you can see from this is that, as we talked about, the algorithm is finding the small factor way more often than it's finding the big factor. So namely, it's finding the 1,200-ish factor a lot more frequently than it's finding the 5,000-ish factor. And just like we would expect from our discussion of the collision finding algorithm in general, the amount of iterations that this algorithm is going to before it finds the collision is varied. In some cases, it finds it after 15 iterations. In some cases, it finds it after 80-something iterations. But again, the number of iterations is always staying much, much smaller than 1,277, which would be the number of iterations it would have taken to find this factorization using trial division. Now, lest you think we spent all of this time trying to impressively factor 8-digit numbers, I'll flip up the size here, so now we're factoring 20-digit numbers instead. And you'll see that this algorithm is still just tearing through 20-digit numbers. 20-digit numbers are probably about the cap of what you could do with trial division, even if you were pretty smart about it. Sage will get really mad at you if you try and loop over something much more than this time. In fact, it might actually not let you get much past even 16-digit numbers, but certainly this is about the realm where trial division is going to be really impractical. But you'll notice Pollard row is just tearing through these. And again, remember what you should be comparing is this number of steps here, this number of GCD calculations that it did, with the number of divisions you would have to do in order to find this by a trial division, which would be something more on the order of this. Now we're up to 24-digit numbers, and 24-digit numbers, I think, are just never going to get found by trial division. These are sort of way beyond the reasonable iteration of trial division. Notice 24-digit numbers, we're now talking about something that's going to take 100 times as long to find with trial division as the previous example when we were talking about 20-digit numbers. But you can see these all pop up. And this is where it's now taking a perceptible amount of time, but still getting done. Now, my experience suggests that, at least with my implementation of this algorithm, about the most you're going to do that's going to be friendly for a video is something in the vicinity of a 30-digit number. And so if we wait a bit, it will probably go ahead and kick out the factorization of this, but it'll take a while. But if you go much past 30 digits, it's pretty rapidly going to enter the realm where it's taking over an hour to factor, and it's not going to take much for Sage to eventually say, no, that you're just taking too many cycles on our server, we're not going to let you do that. If you really want to do this, do it on your own computer. Now, while this again chugs along, one thing I want to point out is at no point in any of these examples that I've shown you has the algorithm failed. In fact, in just a minute, I'll go ahead and pull up an example just to show you the algorithm really can fail, but the algorithm is actually much, much more likely to fail for factoring very small numbers than factoring very large numbers. And the reason for that is that in order for the algorithm to fail, remember what has to happen is that the first collision, mod p, happens at exactly the same step as the first collision mod q, if p and q are the two prime factors of n. And it's just pretty unlikely when the first collision is happening sometime around 10,000, 50,000 steps that you get so unlucky that the first collision happens for both of those prime factors at exactly the same point. And even if you do get so spectacularly unlucky that that happens, you could just go back and run the algorithm again, and that time it almost certainly won't happen. And I now see I've talked long enough that, in fact, we've successfully completed one factorization of a 30-digit number. Again, really, compare this number of iterations that we had to run through with the number of times you would have to loop through trial division in order to factor this number. And I think you will believe that there is no realistic way that you could factor this number via trial division. To show you that this algorithm really does sometimes fail, I'm going to go ahead and run this 50 times on the number 2047. Now, 2047 is not a particularly impressively large number. It's 23 times 89. But you can see how a collision mod 23 and a collision mod 89 might plausibly some percentage of the time coincide. So you can see here one of these iterations here, this algorithm failed. And so actually, if you look, only twice out of these 50 did the algorithm fail, even for numbers this small. So again, it's one of those things. It can happen. It's pretty unlikely. To wrap up this algorithm, it sort of feels like if you summarize this in your head, at least it always feels like this to me, like this algorithm is kind of saying, well, just calculate the GCD of your number with a bunch of things, and eventually you'll get lucky and you'll factor the number. And in some very broad sense, that's true. But you can convince yourself if you really did that, if you just calculated some random GCDs with your number until you found a factor, that's really going to take you exactly the same amount of time as trial division. You're just allowing yourself to get lucky in a different order than trial division. So really, the thing that makes this hum, the thing that really makes this fast, is the rapid collision detection that comes from this Pollard-Rowe piece, where you're able to take advantage of the fact that there are collisions mod p, and then you're able to accelerate finding them in a way that you couldn't if you were just randomly generating these things.